Hey everybody, welcome to chapter 19, part 3. So now we're going to look at how cardiac muscle is put together and how it allows for the conduction of the muscle contraction. So cardiac muscle, we've talked about it back when we were talking about muscle tissue, and we talked a lot about skeletal muscle, then we talked a little bit about cardiac and smooth muscle. If you remember, cardiac muscle is considered a striated muscle, but it's involuntary, so we don't have control over it. A major difference between cardiac and skeletal muscle, other than it being involuntary, is that it contains these structures called intercalated discs. You can see one there, you can see one there. There's another one right there. These intercalated discs contain desmosomes, which are junctions that hold muscles together, the muscle fibers together, and they decrease the stress. So they help maintain the muscle contraction without having the muscle fibers rip apart. And then we have these tiny little gap junctions also. Gap junctions allow the muscle fibers to send signals from one cell to another. So when the skeletal or when the cardiac muscle gets the stimulus to contract, that stimulus can move from the atria down to the ventricles and everything will contract. And so this is just showing the cardiac muscle, and you can see the intercalated discs and everything. So what are the cells that contract? They're called myocardial contractile cells. So we have both contractile cells and then we have conducting cells. Contractile cells are the cells that actually contract, that actually cause the muscle contraction. The conducting cells are these cells that actually produce the action potential that moves throughout the entire muscle. So when we're looking at the conducting cells, we start out with the sinoatrial node. Sinoatrial node is in the right atrium, and it is continuously depolarizing and sending signals. About every 0.8 seconds, it depolarizes and sends signals. The signals move from the sinoatrial node into the atrioventricular node, and then also over to the right or the left atrium. From the atrioventricular node, the signal moves down the atrioventricular bundle to the bundle branches. The bundle branches move to the right and the left ventricles, and they end in these little tiny fibers called Purkinje fibers. And so you have an entire conduction of that action potential from the SA node all the way to the Purkinje fibers, and this occurs about every 0.8 seconds. And so SA node starts the information. So there's your SA node. Depolarization starts there and it starts spreading down to the AV node as well as over to the left atrium. This is going to bring the action potential to the AV node and cause the atria both to be able to contract. Then the AV node is going to send signals down to the AV bundle. Okay, I don't know. Hold on a second. Sorry about that. I don't know why I had the words the, so I just fixed it. So from the SA node, the impulse moves to the AV node. Once it hits the AV node, there's a delay. So the AV node doesn't fire immediately. It takes about 100 milliseconds and then it's going to fire. And this is going to send signals down through the AV bundle to the bundle branches. Once it spreads to the bundle branches, then the impulse is going to spread through the ventricles to those Purkinje fibers. And at that point, the ventricle will contract. And then we start over again. So let's look at the action potential at the SA node, and then we'll look at the action potential at those contractile cells. So in the SA node, we're going to have the membrane potential be brought up from around a negative 80 to 90 up to a negative 40, which is threshold. So this happens because we have sodium moving in, slowly moving in. This brings us up to that negative 40, which is threshold. And as soon as we hit threshold, sodium channels open, but also calcium ions are going to start flooding in. So you have calcium channels open. And that brings us very rapidly up to about a positive 20 millivolts. And so that's where that action potential is. As soon as we hit about positive 20 millivolts, sodium channels close, calcium channels close, and now we have potassium channels opening and potassium rushes out. This brings us back down to a more resting membrane potential. So a similar process occurs in the contractile cells, except that calcium, once you hit that negative 40 millivolts, you're going to have rapid depolarization, and that rapid depolarization occurs as potassium rushes in, but calcium channels are a little bit slower in those contractile cells, and so calcium moves in slower, and at the same time potassium is starting to rush out. So we have this long plateau phase because we have a lot of calcium coming in and we have potassium moving out. So that leaves us with this longer phase before repolarization occurs. And so this occurs about, like I said, the SA node can fire about every 0.8 seconds. So it has the ability to fire about every 80 or about 80 to 100 times per minute. Now, remember that a normal heart beats about 70 times per minute. What that means is that though our SA node can fire as often as 80 to 100 times per minute, it typically does not fire that fast. And that slower firing is due to the vagus nerve. So some parasympathetic innervation to the SA node actually slows our heart down. So though we don't use or need our nervous system to tell our heart to fire, it does help in controlling the heart rate. If the SA node is not functioning properly, then another conducting cell can fire in its place, can send signals. And so these are called ectopic pacemakers. The default ectopic pacemaker is the AV node. And if the AV node is firing, then you're going to have a heart rate of about 40 to 50 beats per minute. That's fast enough to sustain life, but it wouldn't allow you to do as much. So in general, these people would probably be more lethargic and not be able to do as much. If the AV node and the SA node are both not functioning, the AV bundle can fire. If that happens, the inherent rhythm would be about 30 to 40 beats. And this could sustain your life for a short period, but eventually you would have to get a pacemaker put in, like a manufactured pacemaker put in. Bundle branches and Purkinje fibers can also fire, but not good enough to sustain life. So when our heart is beating, we can actually use an EKG or an ECG, however you want to write it, um, to see that action potential in a physical readout. And that can tell us a lot about how healthy our heart is. So there are 5 different points that we typically see on an EKG. There's a P wave, which is this right here. This is when the atria depolarize. Then we have a Q, R, and S complex. So 3 points right here where we see depolarization of the ventricles. And then we have that T wave over here, which is the repolarization of the ventricles. There's also a PQ interval, and you can see it over here probably better. You have an ST segment that can tell you if your atria or your ventricles aren't firing properly. So the PR interval shows the beginning of the atrial depolarization to the QRS complex. And we typically read to the R, so from the P to the R, to actually look at when the atria fire to when the ventricles fire. A delay from the SA node or the AV node would be seen in this area, okay? And so it might show that there's not, or that there's a longer period between the atria and ventricles depolarizing. The QT interval, which you see over here, shows the ending of ventricular repolarization. So as soon as we hit that from the Q to the T, we have the ventricular depolarization and repolarization. And so here you can kind of see this takes the conduction system and the EKG and puts them together. So here where you have depolarization, so at first we just have a resting heart. We have depolarization of the SA node. That's right here. You can see that right here. Then we have the atria contract, pushing blood down here, and the AV node is getting ready to contract because the stimulus got to the AV, but remember there's a short delay between the AV node receiving the information and the AV node firing. So that's this PR complex. And then, or PR interval, I'm sorry. Then the AV node fires, sending a signal down to the AV bundle and the bundle branches, and that's right here, QRS, right here, complex. The ventricles contract, and so the ST segment, or the QT segment, I'm sorry, occurs when the ventricles contract to when the ventricles are going to undergo repolarization. And so here we hit ventricular repolarization, and that's that T wave. I'm going to stop here because it's been almost 14 minutes, and we'll get into how to run an EKG, okay?